Good day, everyone. I trust that we're all doing great. So, just like I promised in the previous video, we are going to be taking further examples on Picard's iterative method. But before I continue, I would like to do a brief recap of what we learned in the previous video. So we said Picard's iterative method is an approximate method for getting the solution of differential equations of the form dy dx is equal to a function in x and y when y is equal to y naught at x is equal to x naught. So recall that we rearrange the differential equation to give dy is equal to function in x and y dx. Then we went ahead to integrate both sides using the limits. Integral of dy between y naught and y now became the integral of f x comma y dx between x naught and x. On integrating the left hand side, we have y within the limits y naught and y is equal to the integral within the limits x naught and x of the given function with respect to x. So now we have y minus y naught on applying the limits will be equal to the integral between x naught and x of f x comma y dx. So we have our y to be equal to y naught plus the integral between x naught and x of f x comma y dx. Now recall that we said after we have been given the value of y naught and x naught, we can be asked to find the value of y1, can be asked to find the value of y2. So we can write this equation in the general form as yn is equal to y naught plus the integral between x naught and x of f x comma yn minus 1 dx. So this gives for y1, for example, it becomes y1 is equal to y naught plus integral between x naught and x of f x comma y naught dx. Also, y2 is equal to y naught plus integral between x naught and x of f x comma y1 dx. And it goes on and on like that. So we can do the same thing for y3, y4, y5 as much as we can. So now let's go on to solve another example on Picard's iterative method. This is slightly different from what we have been doing so far. So the question goes thus. Using the Picard's iterative method, so using the Picard's iteration method, find the approximate solution to the initial value problem y prime is equal to x squared plus y squared. Given that the value of y at x is equal to 0 is equal to 0. So now let's write our general solution. Our general solution is yn is equal to y naught plus the integral between x naught and x of f x comma y n minus 1 dx. Unlike the others where we have to find a value, in this case, we are seeking to find the solution to the differential equation y prime is equal to x squared plus y squared. So unlike the other solutions that we have been doing, we've just been getting the value of the function at a particular point. But now we need the actual function. So we just have to keep iterating till however we desire. So sometimes in objective questions, you will be told where to stop. or from the options you can decipher where to stop. But in case you're not told where to stop, you can just keep iterating, because the more you iterate, the closer you are to the actual answer. So in this case, let's do about 3 iterations. So y1 now will be equal to y naught plus the integral between x naught and x of f x comma y naught dx. So now we have our y1 to be y1 to be equal to our y naught, we were told that it was 0, plus our x naught is also 0, of f x comma y naught dx. And this is equivalent to the integral between 0 and x of f x comma y naught dx. So our y1 now becomes the integral between limits 0 and x of the function we were given is x squared plus y squared. But in this case, since we are told to substitute y naught in the place of y, our y naught is 0, so that's x squared plus 0 squared with respect to x. So we'll be having the integral between 0 and x of x squared with respect to x. So our y1 now becomes integral between 0 and x squared with respect to x. And this gives us x cubed over 3 between 0 and x. So we have x cubed over 3 minus 0 raised to power 3 divided by 3. So our y1 automatically becomes x cubed divided by 3. So we have our value for y1 that way. Now let's go on to do the second iteration. Now remember that the more you iterate, the more accurate your answer becomes. So let's write our formula for the second term. y2 now becomes y naught plus the integral between 0 and x of f x comma y1 dx. Notice that in the first iteration, we used our fx comma y naught. But in this case, we are using our fx comma y1 because our n now is 2. So we have our y2 to be equal to 0 plus the integral between 0 and x of x squared plus, now we substitute y1, which is x cubed over 3, x cubed over 3 all squared with respect to x. So our y2 now becomes the integral between 0 and x of x squared plus x raised to power 6 divided by 9 with respect to x. So on integrating, we now have x raised to power 3 divided by 3 plus x raised to power 7 divided by 7 multiplied by 9 between 0 and x. Now, on applying the limits, we get x cubed all over 3 plus x raised to power 7 all over 63 minus 0 raised to power 3 divided by 3 plus 0 raised to power 7 divided by 63. So we have our y2 now to be x cubed divided by 3 plus x raised to power 7 divided by 63. So if you notice, our y1 was just x cubed divided by 3. But now we have our y2 to be equal to x cubed divided by 3 plus x raised to power 7 divided by 63. I think it's obvious that our y2 is going to be more accurate than our y1 as an answer, because we now have an additional term, x cubed divided by 3, showing there. So if we have to substitute our value of x into y1 alone, we are going to have an answer that is fairly accurate. But on substituting it into our y2, we are going to be having an answer that is even more accurate than the one we have right now. So we expect that our third iteration will be even more accurate. So let's see how that turns out. So let's write our general formula for y3. Our y3 now becomes y naught plus the integral between 0 and x of fx comma y2 in this case with respect to x. So our y3 now becomes y3 will be equal to 0 plus the integral between 0 and x of fx comma y2 dx. And that's the integral between 0 and x of fx comma y2 dx. So let's substitute. Our y3 now becomes integral between 0 and x squared plus y2 squared. Remember, we are substituting y2 for y with respect to x. So this becomes integral from 0 to x of x squared plus x cubed divided by 3 plus x raised to power 7 divided by 63 all squared with respect to x. So we have our y3 now to be the integral from 0 to x of x squared plus x raised to power 6 divided by 9 plus x raised to power 14 divided by 3,969. This is me expanding the brackets for the y2. X raised to power 14 divided by 3,969 plus 2x raised to power 10 divided by 189. So we are integrating all this with respect to x. Our y3 now becomes x raised to power 3 divided by 3 plus x raised to power 7 divided by 9 multiplied by 7 plus x raised to power 15 divided by 15 multiplied by 3,969. Oh, sorry, I made a mistake writing 3,963. Let me erase that up. Let me just write every one of that. So I have x raised to power 14 divided by 3,969, then plus 2x raised to power 10 divided by 89. So the last time we now have plus 2x raised to power 11 divided by 11 multiplied by 189, all within the limit 0 and x. So we have our y3 now to be equal to x cubed all over 3 plus x raised to power 7 divided by 63 plus 2x raised to power 11 divided by 2079 plus x raised to power 15 divided by 59,535. So this is what we have as our final answer for y3. Remember I said we are going to be doing just 3 iterations. So if you check the trend, y1, y2, y3, we can see that y3 is the most accurate of the 3 results that we have. And that's expected because the more we iterate, the closer we get to the answer. So that's the basic principle behind Picard's iteration. Let's take another example. This one is going to be slightly easier. We'll just be doing about 2 iterations just to make it better. The idea is just to make us understand how this thing actually works. How does the principle work? The moment we are able to understand that, then Picard's iteration is a very, very straightforward method to use. So let's take a second example. So in the second example, we are asked to use Picard's iteration method to find the approximate solution of the initial value problem y prime is equal to 1 plus y squared plus x cubed. Given that y naught is equal to minus 4, that is, the y when x is equal to 0 is equal to minus 4. So this is also a very, very easy question to do. So we have, let's write our general formula. Our y naught, y1, sorry, is equal to y naught plus the integral between 0 and x of f x comma y naught dx. So our fx comma y in this case is 1 plus y squared plus x raised to power 3. So our y naught will be equal to minus 4. Our x naught is equal to 0. So we have y1 will be equal to minus 4 plus the integral between 0 and x of 1 plus y1 squared plus x raised to power 3 with respect to x. So our y1 now becomes minus 4 plus the integral between 0 and x of 1 plus, sorry, not y1, it's y not here. 1 plus minus 4 squared plus x raised to power 3 with respect to x. So our y1 now becomes minus 4 plus the integral between 0 and x of 1 plus 16 plus x cubed with respect to x. So that gives us y1 is equal to minus 4 plus integral between 0 and x of 17 plus x cubed with respect to x. And we have the answer as minus 4 plus 17x plus x raised to power 4 divided by 4 between 0 and x. So our y1 now becomes minus 4 plus 17x plus x raised to power 4 divided by 4. So that's our first iteration. To get our second iteration, we just go ahead to write our general formula y2 is equal to y naught plus the integral from 0 to x of f x comma y1 with respect to x. So in this case, we now substitute our value of y1, which is minus 4 plus 17x plus x raised to power 4 divided by 4, in the original function 1 plus y squared plus x cubed. And on evaluating that, we are going to get our result. So, with this, we've come to the end of the Picard's iterative method. And I hope I've been able to make you understand how the method actually works to obtain the solution of differential equations of the form dy dx is equal to a function of x and y, given the initial conditions, that is the value of y when x is at a particular value initially. Thank you very much for watching this video.